Hello everyone, let me start with a question. We all know that if you drop an object, it accelerates at 9.8 meters per second squared. But here's the puzzle. How do we actually know how strong gravity is? Not just on Earth, but everywhere in the universe. For that, we need a number called the gravitational constant, represented by the letter G. It appears in Newton's law of gravitation. F equals G multiplied by m1 multiplied by m2 divided by r squared. Unlike G, which you can measure by dropping a ball and timing it, G cannot be measured directly from falling objects. Its value had to be determined by experiment. The first person to do this successfully was Henry Cavendish back in 1798, and his experiment is legendary. He essentially managed to weigh the Earth. Let's see how.
Cavendish designed a very delicate instrument called the torsion balance. Imagine a light horizontal bar suspended by a thin wire. At the ends of the bar, two small lead spheres are attached. Now bring two massive lead spheres close to these smaller ones. The big spheres attract the small ones gravitationally, ever so slightly. This tiny pull twists the wire, and the bar rotates until the restoring torque of the wire balances the gravitational torque. The key is this: the amount of twist, measured by the angle theta, is directly related to the tiny gravitational force between the spheres. As you see in the diagram, the bar rotates slightly when the big spheres are shifted around the small ones. This was the first time humans could detect the incredibly weak gravitational attraction between ordinary objects in a lab.
So, what's the force between a large sphere and a small one? It's given by the familiar formula, F equals G multiplied by capital M multiplied by small m, divided by d squared, where d is the distance between their centers. This force is minuscule, around 10 to the power of minus 10 newtons. To put that in perspective, it's weaker than the weight of a mosquito's wing. Now, since the small spheres are at the ends of a bar of length L, this force produces a torque equal to F multiplied by L. At equilibrium, this gravitational torque is balanced by the restoring torque from the twisted wire. Look at the diagram. The small spheres are pulled towards the large ones, creating a torque about the center. So by measuring that tiny angle of twist, we can actually link it back to the value of G. Let's connect all the pieces with equations. The restoring torque of the wire is tau equals kappa multiplied by theta, where kappa is the torsional constant of the wire. At equilibrium, restoring torque equals gravitational torque. So, kappa theta equals G multiplied by m divided by d squared multiplied by L. Rearranging this, we get G equals kappa theta multiplied by d squared divided by m multiplied by L. In the diagram, notice how angle theta, bar length L, and distance d all play roles in calculating G. That's the genius of Cavendish's method, measuring a tiny twist to reveal the strength of gravity itself. Of course, Cavendish's measurement was just the beginning. Over the years, scientists have refined the experiment with better apparatus. Today, the accepted value of the gravitational constant is 6.67 times 10 raised to the power minus 11 Newton meter squared per kilogram squared. Interestingly, G remains one of the least precisely known constants in physics. Its uncertainty is still larger than that of other constants like the speed of light or Planck's constant. But despite this, knowing G allows us to calculate the mass of Earth, the Moon, and even distant planets. Without G, our understanding of celestial mechanics would be incomplete.
Let's apply this. Suppose in Cavendish's experiment, we know the mass of the large sphere m, the mass of the small sphere m, the separation d, the bar length L, the torsional constant kappa, and the measured angle theta. We use the relation G equals kappa multiplied by theta multiplied by d squared divided by m multiplied by L. If we plug in typical lab values, the calculation comes out close to 6.67 times 10 to the power minus 11 in the correct units. In the diagram, all the quantities m, l, d, and angle theta are marked clearly. It's incredible that from such a tabletop setup, we can determine the constant that governs the motion of stars and galaxies. So let's wrap this up. The gravitational constant G sets the strength of gravity across the universe. Cavendish's torsion balance experiment in 1798 was the first to measure it, and since then we've refined the value to 6.67 times 10 to the power minus 11. Knowing G lets us determine the mass of the Earth and other celestial bodies, making it a cornerstone of astrophysics and planetary science. Summary infographic of Cavendish's experiment and the modern value of G. So the next time you hear the phrase weighing the Earth, remember, it was Cavendish's experiment with a twisting wire and a pair of lead balls that made it possible. I hope you enjoyed this exploration of the gravitational constant. See you in the next session with another fascinating journey into the world of physics.